Anyway, so just to recap again, on last day's class, we had completed what we call as the EGC or equal gain combiners, and we have observed that with respect to difference being in the weight factor or the optimal weight factor in terms of uh, the portion on with comparison to the EGC, let me just take that EGC one. I think it is this one. So we have done this as well as here one small like not mistake, but there was a problem here. I think I have given you this equation on last day, and this bracket was only first part. So make sure the bracket is whole bracket. Okay, just if you have written it down, although the PDF that I'll upload it will have it, but since you people have written it down, please make sure that the bracket is whole bracket in both the cases. I think in the previous one it was only till like it was missed. Like as far as the writing is concerned, it was a mistake. So the whole bracket, okay, that you please keep a note of. All right. So this was where we ended our discussion. In fact, with MRC, where I told you that this is the average BR or the exact expression for average BR for MRC and or even for multi-path multi-antenna system for that matter. This is a generic equation, in fact. Now, but the problem here is that when we go for more number of antennas, the calculation will become a little bit difficult in terms of if you don't know about the SNR. Suppose this equation you are trying to write and you want to mention in this way that given a particular BR, I'll show you one question today itself. Given a particular BR, suppose 10 to the power 6 minus 6 something value, you want to find out that what should be the requisite SNR for it. So the reverse calculation using this formula will become very, very difficult. Like my question is, suppose I want to maintain and 10 to the power minus 6, suppose 5 into 10 to the power minus 6 average BR for this particular system, find out what should be the necessary SNR which is required. Now, basically that means that you have to do an inverse calculation, and suppose in this case, I am considering that L is equal to 4. We have all done in lab that L equals to 4 is a possibility that we have 4 receiver antennas at the end. But if you substitute L equals to 4 in this equation, then you can see here 1 minus delta whole to the power 4 is coming. And you can see this delta is again given by this SNR plus 2 SNR. So it becomes very complicated to solve. Alright, so that is the main problem that we usually take this exact solution to an approximate solution. And that is where I told you to write down a factor which was 2L. Can anyone tell me what was it? 2L minus 1 CL, then 1 by 2 SNR whole to the power L. Correct. So this was the expression which I considered, and that the approximate equation also is ideally used. It's very similar. You remember the expression I told you that there is an approximate solution to the Q function, half of e to the power minus x square by 2. So that is also, it will give you very similar answer, but not exact, but it is similar. I'll solve a question today itself with both the equation. You will find that they are very, very similar. All right. So keeping that in mind, we ended up our discussion with MRC, and we found out that MRC will provide a better performance compared to a conventional wireless scenario which is CISO communication. And we have also observed in our lab also now with all the batches almost done, I think 2 batches at least to have done, that MRC is providing a much better performance compared to EGC in fact. All right. So keeping that in mind, we went to EGC. I think this is not EGC. Achha, let me open the EGC also. I think it is. Yeah, I can. So many files are there, na? Wow. Yeah, this is the EGC document. So if you remember in EGC, we found out that with all the other elements together, we found out that the SNR part is given by the summation of HI square, where HI is all the complex coefficient and its absolute values. In fact, this also we have done in lab to prove it for that matter. And the only difference being that we have an L factor which comes in at the bottom of your screen. So you have an L factor which comes in over here. In fact, that makes the overall performance of SNR improvement to be little low compared to what we had for MRC. Alright, so that is what we have found out. in fact, keeping that in mind, I have also given you the optimal weight factors, and which is given over here, how the optimal weight factors can be calculated. And finally, we achieve the factor where again an approximate solution for SNR EGC can be estimated by 1 plus L minus 1 into pi by 4 into SNR, which is relatively simpler to understand or simpler to consider with respect to this particular element. Okay, so it is much simpler in that way, because the complex term doesn't exist anymore. We can just substitute the L, which is the number of receiver antenna, and we can get a approximate EGC value of SNR. In your numericals also, when you are going to solve it, you try to identify whether the requisite information is provided or not. If not provided, don't try to over exaggerate and over complicate things. You find out that whether the elements which you require for an approximate solution is present or not. If suppose a given question L is present and you don't have any information about H, then it is directly implying that you have to use this equation. But if suppose the other way around, H is provided and you want to find out, then most probably the exact equation would be sufficient. So that is how we should do it. So let us try to solve a few more questions. I think I'll take that whiteboard and I'll give you the question on that. So the first question that we are taking today is something like, I'll try to write it down. So given H vector, that is the complex multipath, is given by 1 plus J and 2 minus 2J. Okay, 1 plus J and 1 minus 2J. Let me just rewrite this. This is 2J. Alright, so this is given, that given the H matrix is given by this, and SNR is 20 dB. Okay. So the question is, find the SNR MRC and BER MRC. Find SNR MRC and BER MRC. Can you take 1 minute to solve it with the equations that you already have with you? I'll just set up this color a little bit. Okay. Okay. So what are the equations of H is given to us? So what we have to find out is SNR MRC. So if you remember the SNR MRC formula that we have, SNR MRC was nothing but norm of H square into SNR. So this was the equation where SNR, always remember, please mention this SNR in linear scale. Even in lab also I did that, but just for our understanding, let me write it down as SNR linear. Always remember it. Don't put the dB directly over here. Although it is given in 20 dB, it will always be in terms of linear scale. So please mention that accordingly. Alright. So this is the formula. So linear part is, I think it can be taken care of quite easily. So if I do it parallelly, so your SNR is given in dB scale and it is in 20 dB. So you take 10 log of x equals to 20. Okay. So your x is nothing but 10 to the power 2, which is 100. So that's your linear scale value. Okay. It is a linear value of the 20 dB that we are talking about. So that is done. Now we come to the norm part. So let me just do that as well. So the norm part is usually calculated as square root of absolute value of H1 square. Sorry, this is just, I have to rewrite. The bracket is, so it is H1 absolute square plus H2 square, like this. Alright, so given the fact that you have H1 and H2 over here. So H1 is indicating as 1 plus J and H2 is represented by 2 minus 2J. Basically, it is two links. If you remember the block diagram, if you visualize the block diagram, we had two paths. So the two path is indicated by 1 plus Ij and 2 minus Ij. So that is basically my, so this is my H1 and this is my H2. Alright. So if this is the scenario, so let us put the values in. So let me just put the values. So H1 and all, if we take the absolute values of it. So it is 1 square plus 1 square, because you can see 1 plus 1j. So basically 1 square plus 1 square plus 2 square plus 2 square. So we take the magnitude of versions which are present over here. The real imaginary is the absolute value. So that's why 2 square and 2 square that comes in over here. And if you solve this, the final expression that you are getting is 3.162. Alright. So this is where we are getting 3.162. Now we know SNR is 100 already. So let us have SNR MRC as well. So SNR MRC is nothing but H square. So this is basically, this is to be in square. So ideally we can have 3.162. In fact, what we can do is, if I take square here, can you do this calculation a little bit? I think I missed the square here. Actually, 3.162 is itself squared value. Can you please do this internally? Can you do it? Root 10, nah? That's what. So 3.162 is the square itself, I think. So this will be coming as root 10. So this value is ideally H square. So when you take the square of it, 3.162, that is root 10. So square, take the, how much? 10 only, right? Okay. So this I don't need to. Okay. This is 3.162. I have written it twice. Okay. Got it. So let me just write it down here. So we have 10 multiplied by 100. So we are getting 1000 over here. Now we have to, this is not in dB. This is in linear scale. You have to convert that again. So if you convert this in dB scale, you are getting a 30 dB of answer. Please mention that this is not in dB scale. That's why I have written dB and I've crossed it, just to make you understand that the answer that you are getting, because this is the linear scale. Because this is where you will make the mistake. I know that even if I tell you, but you will make the mistake. So this is linear scale. So the answer is in linear scale. Don't write in dB. So convert that to dB again using 10 log of the whole value and you will get 30 dB. So your answer is, like for SNR MRC with the particular scenario, we are getting an improvement from 20 dB to a 30 dB. This in fact resembles the same outcome which we have observed in our lab as well. If you can give the same set of values over there, you should be getting the same answer in fact in lab. So this is about the SNR part. Now can you do me the PER MRC what you are getting? PER MRC, what is the value of it? PER MRC equation. What will be PER MRC equation which you have followed? Where is L? Where is your L here? Where? How do I know that? These are two antenna. This is not antenna. This is two path. Where is the value of A? This is H1, H2. Does that give you any information about L? L is nothing. L is about the number of antennas. Right? So ideally, even if this is provided to you, like you said, we can use the formula directly as 2L minus 1 CL 1 by 2 SNR whole to the power L. We can use that. How much you are getting? Tell me if anyone has done it. 7.5 into minus 5. Okay, this is what the value is. So L is equal to 2. Here we are assuming, since there are two paths. But is there any other alternative solution to this? If suppose, my question is, everyone please understand this carefully. PER MRC, we have an equation of this. But remember, this expression that you are looking at, although you are using it here, but this is primarily valid when SNR is very high. This approximated value will only come in when SNR is very high, but here it is around 20 dB. So ideally, this is not exactly correct, but still we can consider that, okay, we have an answer for it. But is there any alternative to solve it without going into this equation itself? No, we have some other element, other equation. Do you remember this equation by any chance? PER is given by, in general, Q function of square root SNR. That was also BR, right? And I told you this SNR value will go on changing itself based on what our formulas are. Right? So if this is the scenario, if suppose I take this as a scenario, for our case, it is Q of square root of SNR AMR C. That's all. Because Q SNR MRC, we have just now found out. What my point is, you can reuse what you already know instead of solving it something which is not there. Here the assumption is there that L is equal to 2. But to keep it simple, we can use this formula where we can replace the SNR by SNR MRC and we can substitute it over here and you will get a value like Q of 31.622, something like this. Now the point here is what you can say, that sir, where will I get Q function? That is where you get the approximate solution, half of e to the power minus x square by 2, which can be done in calculators, which is not a problem. Right? So if you do this calculation, you will also get a very similar result to that of 7.5. In fact, this is coming as 9.2 into 10 to the power minus 22, something like that it's coming. In Q function, if you do it. This value, if you do it, it is coming around 9.2 into 10 to the power minus 22, like this order, which is very, very low. Why this is coming? Because we have taken the exact solution of it. Which you have taken is an approximate solution, because remember this is primarily valid, the one that L minus 1, primarily valid when we know about L first, and second, this is primarily valid when SNR is very high, which in this case is not. So ideally this is not the correct solution, but anyway we are getting around 10 to the power minus 5, which is also justifiable solution for that matter. Am I clear with this? What the decision we have made. Both of them are correct, but this one, the second one that I have done, is more accurate in that way because we have taken or utilized what we have found out in our calculation rather than taking some assumption which is not there in the question itself. Right? It is not explicitly mentioned that there are two antennas in the question, but we are assuming it that there are H1, H2. So it is assumed that there is two paths over there. Okay, so that is the assumption we are making. So this is some simple question on this, in fact, and you can do it and find out the rest of the calculation for that matter. So this is one of the questions that I thought of telling you. Now let's see another one. This is using the formula that I told you. Is there any doubt here in this question? Please, those who are not keeping it a record of it, later on, please don't come and tell me, sir, what was there in the question I was not able to understand. Let's see this question. Now, you see the question changes. I'll not write it down directly. Compute the BER. Compute the BER for BPSK communication. Don't leave out that whole thing. So, calculate the BER, just the small thing that we need to understand. So, calculate BER. This is the second question. BR equal to how much for a BPSK communication system for a multi-feeding channel with L equals to 4. So this is where explicitly it is mentioned as L equals to 4. Receiver antennas. SNR is 20 dB. SNR is 20 dB for an MRC scenario. Calculate the BR. In this question, nothing is mentioned about the H. It is just mentioned it is a multi-path scenario. That's all. So if this kind of question comes in where L is mentioned to you, we are directly going to use that BR MRC from our assumption 2L minus 1 CL 1 by 2 SNR to the power. We can actually we can actually do the other way around as well. Can you quickly do that and tell me what will happen with the answer with using the approximate solution, and what will happen if I take the exact solution? So I'll just write the first one here. I'll not compute it. You tell me the computation, you can do it. The exact solution, if I write here, because that will give us a very good understanding of it. So 1 minus delta by 2 whole L summation L equals to 0 to L minus 1, L plus small l minus 1, C of L, 1 plus sigma by 2 L. So these are my two equations. I want all of you to please compute it. Just substitute the data. Remember, SNR is in linear scale, and this lambda, if you are using the exact one, is nothing but square root of SNR by 2 plus SNR. Please compute, take your time to finish this thing off. 20 dB. It should be converted to linear. Everything, every equation, wherever you come inside, whenever the SNR is being used, it should be in linear scale. Later on, we have to convert it back, just like we did in lab also. We took it in linear scale, then we converted back to dB. So that is how we should be approaching. Don't substitute directly SNR, whatever the SNR values provided to you over there. Using which one? First one or second one? First one. So first one, we are getting some answer. So first one, someone has calculated. How much? You tell me. How much? 2.18, but you were saying something else, I think. 2.18 into 10 to the power minus 8. Very good. Hopefully this part is known to all of you. How to combine n factorial by k factorial into n minus k factorial. So that's what we have to do. Just go back and check it. Although in this solution, the calculation is done with every step, but try to do that on your own. So basically, in this case, in the first case, if I say, it is like 2 to the 2 into 4 minus 1 C of 4 1 by, the SNR is anyway 100. So 2 into 100 is 200 to the power 4. So this will be the expression. Once you substitute L equals to 4 and your value is SNR is 20 dB. This in linear scale is 100. We have just now calculated in the previous question. So that 100 is kept over here and you can solve it. So this is 8 minus 1. So it is becoming 7 C4 1 by 200 whole to the power 4. That's all. Alright. Even this also can be done for people, anyone, if you have problem. So this is 7 factorial divided by 4 factorial. 7 minus 4 factorial 1 by 200 whole to the power 4. But usually do it this way around and we can get the final answer. So that gives you 2.18 into 10 to the power minus 8. Now can you solve the other way around? The exact solution, what you are getting with the exact solution. The second equation, maybe I'll write it down as first equation and this is my second equation. Anyone? Second equation. 1 minus delta. So you have SNR as 100. So what is your sigma values? So let me take this part. Second equation. So let me take this part 1 by sigma like this. So this is one portion over here. So for that to happen, this value is square root of SNR, which is 100 by 2 plus 100. This is coming from the equation as given here. So we are getting square root of 100 divided by 102, which is around 0.9901. So this factor is 0.9901. So substitute over here. So we get 1 minus 0.9901 divided by 2, and this is coming as 0.0049. Everyone clear with this? What I did is nothing but this. In this equation, there are two factors: 1 minus delta by 2 and 1 plus delta by 2. So you can do one thing, you can also find out what is my 1 plus delta by 2. So 1 plus delta by 2, this also will come as 0.9951. Okay. So in this equation, now we substitute. So let us do that. So after substitution, we'll get something like this. BER exact, VER, we take the exact equation. So exact is nothing but, what will it be? First term, what is the formula? 1 minus, what is my 1 minus value? 1 minus value is 0.049. So what is the formula? 1 minus sigma, 1 minus delta by 2 whole to the power L. So 0.0049 whole to the power L. That's all. Okay, that's all. Now we take the summation part. So summation L equals to 0 to L minus 1. What is my capital L? 4. 4 minus 1 is 3. So 3, 4 plus L minus 1, C of L, and then 1 plus sigma, 1 plus delta by 2. So 0.9951 whole to the power L. So check this. This is nothing but representation of this equation. Same thing, I have written it down with the values. That's all. Now, if I go on expanding it, let this be over here. So the summation part, we'll just have L equals to 0 to that 4L plus 1. So your terms can be something like, check if you can understand this, 3C0, 0.9951 whole to the power 0. Can everyone understand why I did it? Because L starts from 0. So we substitute over here. So L equals to 0 means 4 minus 1, 3. So 3. L equals to 0. So 0. Okay. Then the value 0.995 to the power L. At that point small l is 0. So this is 1 first term plus 4C1 0.9951 whole to the power 1 plus 5C2 0.9951 whole to the power 2 and plus 6C3 0.9951 whole to the power 3. So these are the terms associated with the summation part, and when you include that factor of 0.9951 onto it. Now you have to compute for all these cases in the same manner like we did in the previous case. So these are all combinations. Multiply that factors associated with it. So after you do all this, which is very trivial calculation, I would say, you will get a value of 2.037 into 10 to the power minus 8 as the solution. So if I write it down once again, so in BER, in case of BER, the exact solution, this is coming as 2.037 into 10 to the power minus 8, and BER approximate solution, this is coming as 2.18 into 10 to the power minus 8. What happened? Error? Any? 6. You are getting two values. Which one? Exact. Exact. What you are getting? 2.16. So let it be. I have to recheck then. They are getting some value 2.16 into 10 to the power minus 8. So anyways, the main reason is that you can see the exact and the approximate is almost giving you the correct answer, or almost the order of it. As I kept on telling you, the order is important. It would have been an error if it is 10 to the power minus 8 and the other one you were giving as 10 to the power minus 3. that would be an error. Magnitude wise, we are not bothered much because these are anyway very small values. Okay, so that is not too much concern for it. So this is a question where we are actually comparing both of the PR expression to solve the same. And I intentionally did this problem. The reason is that this is a question where this inside bracket, how it is to be calculated, we can understand that properly. Any doubt over here? How to approach this kind of question? Okay? If in this question, H was mentioned for that matter, and you could have solved the QSNR, we could have done with the BER QSNR calculation as well. But no need for us because we don't need to unnecessarily complicate things over here. Alright? So this is another question on the same order. Now coming to the another aspect of it, this is although it is not exactly a numerical, but this is a fact which you need to know a bit, and that is called as diversity order. Let me just write it down for you. This is just an information which you keep it because this might be useful in some numericals where instead of mentioning L equals to 3 or L equals to 4, the term can be what the diversity order is given by 3 or 4. So you might find that what exactly is diversity order we don't know. You might find confusing. So that's why this is a term associated with diversity order. All right. Just give me 1 minute. I'll just add the my power cable for once. I don't have charge, unfortunately. Just a minute. Okay. So diversity order is nothing but the ratio of bit error rate, probability of bit error rate to that of the SNR value. So this is given in the way, it is expressed usually in the way of limit minus of SNR. Please make a note, you don't need to compute anything, it's just for your understanding. This is given by log of PSNR, which is basically your bit error rate, divided by a log of SNR. This is the ratio. This is usually the expression of a diversity order. Suppose specifically you are asked to find out what is diversity order, then usually we do it this way. But interestingly, some very interesting observation that happens. Okay, so case 1, suppose the case 1 is where we have a seesaw communication. Alright, we have a normal seesaw communication. That means we have a normal multipath scenario. Single antenna at the transmitter, single antenna at the receiver. So, if I do that, does anyone remember this? This formula? PE for a basic wireless scenario is 1 by 2 SNR. At high SNR value, when antenna numbers, when L is equals to 1, that is a seesaw system, we had already derived that in our previous classes, that the probability of error is almost equal to 1 by SNR, or we can say it is 1 by 2 SNR with the exact solution. This is when SNR is very high. Now take this into account and you substitute on this equation. So let me do that. So minus limit SNR tends to infinity, log of 1 by 2 SNR divided by log of SNR. Alright. Now if you rearrange them a little bit more, minus limit SNR, see SNR is infinity, that means SNR is very high. That's what we are assuming. That's why we can assume this one. Okay, now otherwise we cannot do that. So in this bracket we can write log of 2 divided by log of SNR minus log of SNR by log of SNR. We are just rearranging this equation into the factors. Okay. Now if I take the every calculation all together over here, you see this part. Can anyone tell me what will be the value of this part? This part. When SNR tends to infinity, log 2 by log SNR, what will be the value? So this will be equal to a 0. So what we are left with is in the right hand side. So this is basically 1, which is equal to 1. So ideally what we have assumed over here, your case is where L equals to 1. So we have started with the condition that this is a seesaw system where there is one transmitter and one receiver. So the diversity order that we are getting, so this is basically my diversity order, if I call it the D. So D is coming as 1. Right. So basically, number of antenna is equal to the number of diversity or the amount of diversity. Similarly, we can also prove for multipath. It is given here in the course page for the P multi-antenna system. Multi-antenna system, this will be equal to L. So please make a note of it. This can be also derived from the same expression. It is given in the PDF. You can look at it later also. So the conclusion that we are drawing over here is that for a single system, if it is 1, then there is L number of antenna. If it is, this can be called as the diversity of the antenna. So the same question that we have solved right now, this one, we have solved this question right now. I can change this question to that find the BER for a Rayleigh fading scenario given the diversity order is equal to 4. So don't get confused at what exactly is diversity order, whether diversity order and the number of antennas are correct or not. Okay, so that is the reason I gave this information right now to you. Right, so this is another one, and I think we don't have that much time, but still I'll try to squeeze in one more question onto it so that we can at least have some idea. Let me take that. We can do this question. Acha, are we confident about solving this kind of question? You tell me what is the procedure to do it. Okay, compute the SNR required for a BER equals 10 to the power minus 8 and 10 to the power minus 10. Compute the SNR in dB. Question is compute the SNR in dB given that we want to achieve BER of 10 to the power minus 8 or 10 to the power minus 10 for a BPSK system over an AWGN channel. Which formula we are going to use? Can anyone tell me? How we are going to proceed with it? We have already solved questions like this before. First of all, is it an MRC? Is it an EGC? No. Basically, this is not a diversity based question. Because if it was there, then we could have answered with respect to a Rayleigh fading channel. Because then only the multipath will come in. But here it is only mentioning AWGN. So basically it is indicating about a wired scenario, where we had actually started long back. So if you remember, there was a factor that I told you that BER is equal to Q of square root of SNR. Just now, little while back also we have referred to this. So this equation was valid and derived for a wired scenario. Wired means it is an AWGN channel scenario. So in this case, your BER is given as 10 to the power minus 8. So the left hand side of the equation is actually 10 to the power minus 8 equals Q of square root of SNR. But remember, this is in dB. So SNR dB, this is in linear scale. In this equation, this SNR is in linear scale actually. So you just have to compute this. So this can be approximated to half of e to the power minus x square by 2. Or half of e to the power minus SNR linear by 2 and do the necessary changes. Find out what is SNR linear, convert that to dB. So that will be the answer in SNR dB for 10 to the power minus 8. We have already done the question. We had used 10 to the power minus 6 at that point. So similar kind of questions can be expected and can be solved if you had followed all the equations which we have told you. Naturally, as I said, no derivations are required, but the equation, those I have specifically mentioned to you, those are fundamental important equations. And as you can see over here with the questions that we have solved at least, or even some of them I missed, it will be there in the course material. You observe that mostly the two equations are important. One is the BER expression for wired, for wireless, for diversity case, and the SNR expression for wired, for wireless, and for diversity case. Wireless I'm talking about here in terms of CISO, non-diversity scenario. Alright, so only this portion of it, if you can keep a note of it, especially during your CAT 2 where you have a open book scenario, I think at least if you can consolidate those formulas, I think it will be sufficient. Alright, few more questions are there, but due to lack of time, I am not able to solve it. But there are some extra examples also mentioned over here and some to be solved question also mentioned, which are basically influenced by the previous questions which we have done. So if you want to solve them and send it back to me, that saying that, sir, I have done the question, can you please solve it? Can you check it once? Yeah, absolutely, you are welcome to do it. Because remember, in CAT 2, all this type of questions will only appear. Okay? So please prepare and accordingly send it back for feedback. Very good. Yeah. Perfect. Which one? This one? This is general means CISO communication, if you say. This one you are looking at ideally an AWGN scenario. If it is a CISO, that is when you are looking at a wireless scenario, ideally this should be S square into SNR. Remember that A comes in, the random factor that comes in, the probability of deep fade where we have discussed. So this will be A square SNR. If it is MRC, it will become SNR MRC, where SNR MRC is again norm square into SNR. Understand? So that's how the SNR values will change. Alright, so let us stop at this point. So we come back on next day, we solve, we go ahead with this, where we go from receiver diversity, we expand it to the MIMO technologies, where we have multiple antennas at the input and multiple antennas at the output. And let's see how we can figure out the same. Alright, thank you.